Well, thank you, and so good to see you all here, and especially to see the students here. Very exciting time in your life to be studying and learning and seeing the possibilities of what you can do with your life in science and in Buddhism or whatever you choose to study. And I would like to thank Bryce especially for inviting me and my other colleagues here, but also like to I'm very honored to be in your presence, especially the many learned individuals within the Buddhist perspective. So I'm looking forward to learning a great deal from you and having conversations that will help me and understand what I'm going to do as I move forward. The story that I'd like to tell you today, at least to begin with, is to think a little, for me it's been a personal story of understanding physics and how that helps me understand my life. Physics for me is a worldview to some extent in which I think, how do I understand who I am and who I am in the universe in this regard? And physics, my original studies was in quantum optics, and I'm an experimentalist, which means I like to play with toys, really expensive toys. And so I've had a great deal of fun doing that and working with a number of individuals. The story we're going to start with, though, is about quantum mechanics and about classical mechanics. And what I mean by that, I'll show you in just a second here. So here's a length scale from the very big to the very small. In classical physics, we think of all the big things. So that could be galaxies, or it could be planets, or stars. It could be this room, it could be trees, or yourself. So everything big is governed by what we call classical physics. And this is physics that's been understood and been developed for many hundreds of years. But when you get down to things that are very small, and so I'm talking about things on the very left-hand side of this graph, all of a sudden physics changes. And all of the rules that we had for what is understood about what is going on in physics, there's some new set of rules that go up. And these are the quantum rules. And they start when we get down to, thank you. Fantastic. They start when we get down to things that are on the size of atoms. And so I'll talk a little bit about those length scales in just a minute. But we'll just say that when we grow up and when we think about things, it's very intuitive to think about the things that happen at the very large scale. But when you get down to the very small things, things just get weird in just a very strange way. And so one of my favorite physicists, and who was quoted earlier this morning, was Richard Feynman. He's a famous physicist who studied most of the time at Caltech. And he had a quote, which I love, talking about the difference in physics between physics of the very big and of the very small. We know how large objects act, and that's like planets and stars and snowflakes. But things on a small scale just do not act that way. It's a different set of rules. And in fact, one of the things that me and my colleagues will be speaking about over the next couple of days is that these rules imply things that we just don't know about. And so we'll kind of explore that and hopefully explore that from the Buddhist perspective as well. So things of the very big, and so I'm going to start talking a little bit about classical physics. So this is everything from stars and galaxies to leaves to glasses of water, which I now have an empty one, to snowflakes, bits of dust, all obey what we call classical physics. And classical physics pretty much started, or at least formally, with an Italian physicist, although it's been explored in a variety of different ways. This is Galileo from the 1600s. And Galileo dropped a few things off of a tall tower, watched them fall, and made some conclusions about the way that nature is, that had not been made before. And I love one of his phrases here: you cannot teach a man anything, you can only find it to help him find it within himself. And I hope that we, during these next couple of days, can find it within ourselves to learn something about science and learn something about Buddhism and the perspective in which these two interact. All right, so let's think about distance. Let me just see here. So the first concept I'm going to talk about is distance. And I know that you all know what distance is, but I'm going to be a little bit formal about this. Let's see. Can I have you stand up? Just stand right there. That's fine. All right, so if I want to describe where he is, what do I do? I have to make a decision about that. All right, so I'm going to decide, first of all, that there is some place. I'll call this the start. And, okay, I think he's about 4 meters from this side. Does that seem okay? Okay. Stay there for a second. So his distance is 4 meters from the end of the desk. And so we can describe the distance of an object in this case. So we can describe his position when we know some place where we start measuring and then we measure with some sort of length scale. In this case, we use meters. He's about 4 meters from the end of the desk there. Okay, that's great. So now I'm going to ask a second question, which is how precisely do we know his position? So 4 meters seems reasonable. Now I have but I can do better. So precision has to do with something with how we do that. So I have a more precise measuring device. Let's see if I can measure it better. Can I get your help here? Can you come with me? All right. Very fancy, very technical. This is science. I want you to just hold this right here. All right. Okay, he's 4.13 meters. Thank you very much. All right, 4.13. It's just a coincidence that that's what's on the slide. So we made a more precise measurement of his position, and that's great. So we could even do better if we had more precise measurements. Of course, we'd have to decide where the center is and a few other things like that, but we'll just assume that we can do better. In fact, if you have a more and more accurate measuring device, you can, in classical physics, you can determine his position to a somewhat infinite precision. So here's our very fancy laser rangefinder, and he's 4.1325782048. Oh, you get the idea. Very accurately. And classical physics does not limit the precision with which we can know an object, the distance which we know an object. All right? So that's a critical point about classical physics, is that precision is not limited. And so arbitrary precision, we just have to have a good enough ruler for that. Okay? All right. So that's position. Now I'm going to take a slightly different tack here, and I'm going to take, so I have a glass here. What's inside this glass? No, thank you so much. All right, so now there's a great audience here, I tell you. All right, so I'm now going to pour some of the water out. I'm going to take half of the water out, not spill it too much. There we go. A little more. What's inside the glass? Oh, it's still water. Okay. I'm going to pour about half out again. And now what's inside? Oh, let me try it half again. What's inside now? Oh, it's still water. I'm going to do it one more time. What's inside now? A little bit left. Oh, it's still water. It's amazing. Okay, here, I'm going to put these down here. Thank you. So it turns out that it doesn't matter how many times, I have my glass of water here, it doesn't matter how many times, according to classical physics, that I divide it up. I can go down and down again, and I'll always get water if I divide it up. But something changes when you get into the quantum mechanical realm. And the thing that changes is when we get really, really small, we actually find that things are no longer water. You get down to something that's fundamental. And the thing you get down to is what we call molecules or atoms. So here's a representation of an atom. Don't think too carefully about it, but I'll just say that there's a couple of pieces about the atom. So there's 3 basic constituents in an atom. There are electrons, and those are orbiting, so to speak, around the outside of a very small central part. And that central part is the nucleus. The nucleus is composed of protons and neutrons and nothing else. Everything you see in this room, the lights, the room itself, the air, outside, the trees, they're all composed of just these 3 things: electrons, protons, and neutrons. They make up every kind of atom that exists. And so the question, and I've just taken the most simple atom. The simplest atom is hydrogen. It has 1 proton and 1 electron orbiting around the outside, nothing more. Now, these atoms are very, 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 very small. In fact, the distance there we measured, Shunjong, I can't remember. Sunju, thank you. I'm sorry that I'm mispronouncing names. You can mispronounce mine later if that helps you. But the size of an atom is 9 zeros and then a 1. It's really, really small. Okay? And so, but it's so small that we cannot see it with our eyes. In fact, you can't see it with a regular microscope either. And so you might ask the question, and I think it's a valid question, does it really exist if we can't see it? And so the point, though, up until maybe about 40 years or 30 or 40 years ago, we really couldn't see things at the atomic scale at this level. But there was a new invention that was called the scanning tunneling microscope. And in fact, now we can actually see things at atomic scales. And this is, in fact, silicon atoms sitting on a lattice work. So we can actually resolve things that are these very, very small objects. So we know something, and in fact, our understanding of atomic structure has improved significantly. Here's all of the different kinds of atoms. You yourself are composed of hydrogen, carbon, nitrogen, oxygen, little potassium and sodium, and a few other things. But mostly carbon and oxygen and nitrogen and hydrogen. So these are all the atoms. They make up everything that exists that we see, the room, all of that. But again, each one of those is composed only of electrons, protons, and neutrons. All right, let's go to water. As we were dividing up water, we divided it up again and again. If you divide it up to the very bottom, you get one molecule of water. And one molecule of water is composed of an oxygen atom and 2 hydrogen atoms. And so you can see that here pictorially. Hydrogen is 1 proton and 1 electron. Oxygen has 8 electrons and 8 protons, and also has 8 neutrons. And again, the distance here, very small, but the nucleus is even smaller. Just to give you a sense of the size of the nucleus compared to the atom itself, if this room was an atom, very, very small, then this decimal point here, that's about the size of the nucleus compared to the room. It's very, very small. All right, so things are very small and things change. As I mentioned, when we get to quantum mechanics, things change at this small level. Let me introduce one more new topic. So we knew something about matter, we know something about position. So let's talk about energy. Everybody talks about energy, we want to have clean energy. In physics, we have a very specific way of talking about energy, and it has to do with, it's a very important quantity in physics, and it's important because it has a particular property. It is called conserved. And that means we cannot create it, and we cannot destroy it. We can transform it. And so I have a picture here, actually, of lightning. And the way lightning is created is that you have a thunderstorm in which water droplets are being pushed up and down within the cloud, and some of their electrons are scraped off in this physical movement of pushing these water droplets around. When those electrons come off of the atoms, they immediately want to come back, and when they do, they snap back, and the energy of which I pulled them out, it takes me energy to pull those electrons off, but when they come back, that energy has to go someplace. And so it oftentimes goes out in the form of a photon. And a photon was described in some of the display outside here. For thunderclouds, you strip off these electrons and you get a very positive charge on one end of the cloud and a negative charge on the other end. And finally, those electrons and those protons and the charged atoms then conduct, and you get electricity. And those rip off the electrons, and when those electrons recombine with the atoms, they emit photons, and that's what you see when you see lightning. So we've changed mechanical energy of pushing the water droplets up and down in the cloud to visible energy, photons that come out from lightning. All right, so let's take a look back at our hydrogen atom, our simplest atom. And one of the properties here is that if I've got an atom, and I have a model atom right here. It's much bigger than a regular atom. It doesn't look like an atom either. Does that look like an atom? No. But I can make it go around, so then it's fun. So one of the things about what I want to talk about is an electron, which is going to go around. It's at some energy. So there's some energy that makes the electron move around at some distance from the nucleus. So you can think of this copper tube here as the nucleus, and the electron is around the outside. But I could also have that electron a little bit closer. And so it has a different energy there, or I could have it a little closer still, like there. You could also imagine the same thing with planets, for example. So the Earth is moving around the sun. Earth gets pulled towards the sun. But the Earth is not limited in which size the orbit is. It could be this big or this big or this big. There's no limitation in classical physics about the size of the orbit that exists there. And that's the important philosophical point that I want to make sure you understand here, is that there's no limits about what size the orbit can be or it has to be. But I will say that, I'll go back to my atom here, when the electron is in a bigger orbit and it comes down to a smaller orbit, there's a different energy or a difference in energy, and that energy has to go someplace because energy is conserved, and so it comes out in the form of a photon. The photon carries the energy away from the atom. So we have a photon illustrated here with my red squiggly line. I'm not sure why red squiggly lines mean photons, but they do. All right, and you can see these photons using a device. This is called a spectrometer, and you put hydrogen on one side and you look through the other side and you'll see that. All right, so let me go now to my hydrogen atom, and what would we expect from that classical interpretation of an atom? So the electron can have an orbit this big or 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 this big, and so a transition from one orbit to another orbit means that I will get a photon out. Photons have a different color according to their energy. So photons that are very blue, that's high energy photons, and photons that are very red, those are low energy photons. So according to classical theory, it says it doesn't matter what energy or what radius that this electron is sitting at. It could be any radius. And so as a consequence, you should see light coming out in any color because it could make a transition from any bigger to any smaller radius. Doesn't matter. Seems reasonable? You can nod if you like, it helps. No? Okay, good. Thank you. All right, so people started looking at this about a little more than 100 years ago, and they put hydrogen light into a spectrometer, and here's what they saw. In fact, they did not see a continuous spectrum. They saw a discrete spectrum, which is to say that there is only certain photon colors. There's a red one, there's a light blue one, here's some purple ones down here, there's like only 4 there. But they're very discrete, and those are the only ones they saw. And so they scratched their heads for a while, and they thought, you can scratch your head right now if you like, if it helps. And they said, what's going on here? There's something different. And this is when we get back to Feynman's quote, things are different at the quantum scale. And so I won't go into all the details about how they figured out what to do, but they realized that they could explain a hydrogen atom's spectrum by thinking about one particular philosophical point about position. Okay? So if they in fact assume that the position is unknown, but we kind of know where it is, but if we say we don't know exactly where it is, if we make that indeterminate, this allows us to generate the hydrogen spectrum. And I'm going to show you how to do that in a minute. But I want to just point out that this is a philosophical difference. In classical physics, we know where Sonju. I'm going to get this right yet. Maybe. We know where Sonju was. We could say exactly where he was. Sonju? Am I doing this wrong? I'm just killing his name, aren't I? Ah, jeez. All right, well, someday I'll figure this out. So anyway, I know where Bryce is, and I can pronounce his name, so better. So the position in quantum mechanics, we just don't know where it is. In fact, not only do not know where this electron is, in fact, it is unknowable. And this is the critical point. In quantum mechanics, the position of the electron is not knowable. It's not just that we don't know where it is, it's just not knowable. And that is the formulation within quantum mechanics that helps us think about how to solve things like the hydrogen atom and the spectrum from that. So one of the founders of quantum mechanics was a guy by the name of Niels Bohr, and he had a great quote on this one. And he said, if quantum mechanics hasn't profoundly shocked you, then you probably haven't understood it yet. It's just weird. Because the idea that, in fact, that you can't even know where that electron is That's a really different sort of thing. All right. So let's see if we can describe that and why this makes a difference in determining the hydrogen spectrum. There are many other questions that you can understand with this formalism, but we'll just go into the hydrogen atom first. So let me start with my quantum mechanics classroom. All right, so I had 30 students in my quantum mechanics class, and I just took down their ages. And you can see here, I had one student who was 19, two that were 21. I had 8 students that were 23 years old. And there are no students who are 25, and so on and so forth. So the probability that if I took a room and I put all my students inside and I turned the lights off and I came in and I grabbed a student at random and pulled that student out, 8 times out of 30, or about 27% of the time, I would pull out a student who was 23 years old. There are no times when I would go in and grab somebody who was 25 years old. So probability is just the chance that you're going to select something at random in a system there. This is actually how we think a little bit about the position of the electron. There is some chance that we're going to find the electron here, and some chance we'll find it over here. But we don't know for sure what it is. Just like when I have the dark room and I select the student, I'm not sure exactly what their age is, but I know something about what the probability of that age is. All right. So let me introduce one more concept that we need to use in this thing, and that's called a function. This is a mathematical term, and I happen to have a sine function. The reason I have a sine function is that later on we'll see that actually to do quantum mechanics you have to solve a particular equation, and that equation is called the Schrödinger equation. And one of the solutions of the Schrödinger equation, at least in one dimension, is the sine function. So we'll use that and just explore that. So functions are what I think of as input-output devices. I input one thing and I get something out. So the input is something along this line. I could put in 1 or 2 or 3 or 4 or 1.5 or 2.5, whatever I want to put in. And the output would be whatever the blue line is. And so here I put in 1 and I get out 0.84. If I put in, say, 1.5, I get out basically 1. If I put in 0, I get 0. So it's a mathematical description of something. All right, seems reasonable? Now I can think about this in terms of the probability distribution, a function of probability for my students' ages. So here I have my students are probably not 1 year old, but you get the idea. So this is going to be the most likely place that I'll find, and this will be the least likely places. And you can see that the probability is 0 where it crosses the axis here. 0 here, here, and over here. So we have the most likely positions and the least likely positions. All right? Everybody cool so far? Okay. So now let's use that in thinking about atoms. And again, things that are very small. So here I'm going to say that I've got a distance in which we start out at the left-hand side and at the right-hand side. I'm going to say that I'm going to exclude the electron from existing anywhere over here and anywhere over here. We're just going to say that the electron binds it so closely that I cannot see it in those two areas. And so now I have to ask the question, where will my electron be? And again, going back to the fundamental idea that position is probabilistic, or it's indeterminate, how do I put that in there? All right, so, and as I mentioned before, the sine function is actually a solution to this equation that governs quantum mechanics called the Schrödinger equation. All right, so here's a sine wave, and I put it in there. All right, well, this works. It's 0 here, but it's not 0 there. So this particular sine wave will not actually solve this. I have to have it be 0 here, and it has to be 0 there because it's bound in this area. All right? So this one doesn't work, but I can squeeze it together just a little bit. Make sense? All right, that will work. It's exactly the right shape. It's 0 at both ends, and this one particular sine wave will work in there. It turns out that this particular sine wave then has an energy associated with this, associated with that electron in there. There's a couple things about it. One, you're most likely to find the electron right smack dab in the middle of the atom, and you're less likely to find it right at the edges. So this is a probability distribution or probability function. We sometimes call these the wave function. You'll hear that from my colleagues as we talk about this some more. But this is one. So what about the next highest energy level? Remember, I can't go to this one because that one doesn't, it's not zero at the places where I can't have the electrons. So the next one, you can probably guess it, looks like this one. Does that make sense? So it has to be zero at the edges, and so the next one is there. And you can imagine I could have 3 loops, and that would be the next energy. So here are the 2 lowest energy levels. And because of these 2 lowest energy levels, you can now see that energy is, in fact, doesn't have any particularly arbitrary energy value. It, in fact, has discrete values. This first one and the second one. This one won't work. It's not allowed according to the mathematics of solving the Schrödinger equation. So, having these discrete energy levels, that's exactly what happens in the hydrogen atom, is that we have energy levels of a lower energy, and higher energy, and the next highest energy, and so on. And just coming out of the mathematics, you get the solution to the hydrogen atom. And you don't just get it well, you get it extraordinarily well. It's very good. So, the quantum mechanics and the formalism of quantum mechanics based on the indeterminacy of the position gives you solutions to understanding the energy levels of the hydrogen atom. It's a very simple system, but it's fundamental and it underlies most of what we know about physics and chemistry, actually. It only requires that we know something that we determine that probability. All right, so what happens when we change from probability to certainty? And I'll just say that this is before we actually measure the position of the electron. So when we have to assume that we don't know the position of the electron, and in fact, the electron itself, its position is unknowable. But at some point, we actually measure it. We have a device and we can measure that position, and at that time, we know exactly where it is. And so the question is, what happens between when we don't know where it is and when we do know it is? So this is one of the fundamental problems, and we're going to hear a lot about this over the next few days. It's called the measurement problem. So what happens that changes the indeterminacy of the position to a determinate position, to a certain position? So I'm going to just tell you kind of the 3 basic schools of thought of this. And there are more than that, but I'll just say these are kind of how we think about these kinds of things and how we've been taught as physicists to think about these things. So the first one, sometimes called the orthodox view, and that says that that electron, it's not anywhere until we actually measure it. It just doesn't exist in the way that we think about it. We know there's something there, but we can't actually say that it exists any one place. It could be, it's kind of like all places at once, but not really. So this is sometimes called the Copenhagen interpretation, because Niels Bohr and Werner Heisenberg, who were the 2 physicists who were working on quantum mechanics and thinking about this problem, were doing this in Copenhagen. But it's kind of odd because it's like, is the electron there or is it not there? And we don't know the answer to that question. It's an indeterminate question. So that's first school of thought. This is what I got taught when I was taking physics. This is the standard thing, is that the position of the electron is unknown. When you make a measurement, poof, something happens magically and they now know the position. The second school of thought, sometimes called the realist view, says that the particle really is somewhere, but our theory, quantum mechanics, and what we know is somehow incomplete. There's something else about the theory which we don't understand. There's a couple of versions of one is called the pilot wave interpretation, and I think some of my colleagues will talk about that. Another one's called the many worlds interpretation. I don't want to go into the details of that, but they're interesting concepts there. So it's there, but somehow our theory is incorrect. And the third one, which is my favorite, which is kind of how I work, is called the agnostic view. And this basically says that there is this question of where the electron is actually, I don't actually care about that. It's not that I'm lazy. It's just that quantum mechanics is so good, I can just use it and I'll get the right answer about what happens in reality so often. And if I knew where the electron was or I knew something more about it, it's not clear that I would actually know anything more. It wouldn't help me solve real problems any better than what I'm solving now. And so knowing something about this is actually, it's irrelevant for me solving real problems like designing an integrated circuit or understanding the hydrogen atom. It doesn't help me do, that information doesn't help me. So this is sometimes called by physicists the shut up and calculate. And so, and this is, I would say, probably most physicists kind of work on this particular way. They say, nah, that's a really interesting question. I can't understand it. I'm going to ignore it. It's probably not what we want to do here. I think we want to understand something out of it we can. But this is the way a lot of people think about things. All right. So just to kind of recap briefly here. In classical physics, we have three things. One is that the position is absolute. We can figure it out to any precision. Energy is conserved, but it can assume any value. And then the third thing is that matter is infinitely dividable. I can keep cutting that glass of water in half, and I'll keep going down there. How is it different in quantum mechanics? So first of all, the position, it's not only unknown, it's unknowable. And it's determined by probabilistic sort of arguments. Energy is still conserved in quantum mechanics, but in some places it can have discrete values, like in the hydrogen atom. It's not always, but many places. And finally, matter has a fundamental nature to it, these atoms and molecules, and they're made up of fundamental particles. So this is an amazing, amazing theory. It's so good. Here's an example of the precision with which you can do it. This is the actual energy level of the difference in energy between two atomic lines of hydrogen. And it can know it to 16 digits. And that's the most recent measurement, and I'm assuming it will get better, actually. And the theory is so good that it will predict that to amazing precision. There is no other theory, quantum mechanics, there is no other theory than quantum mechanics that will do any better. We've never seen a theory that is as accurate as this one is. So that's amazing. The other thing is it's never been shown to be wrong. Many people have tried and see if there is a hole in it someplace, and there's no experiment that's ever been done to show an error with the theory. So we're really pretty confident about it. Here's an experiment that was used to measure that hydrogen alpha line. So let me just close with two quotes here, just so you get an idea of some of the confusion I think that we feel as physicists. First, this is Schrödinger. This is the one whose name was of the equation that we use to solve quantum mechanics. So he died in 1961, and near the end of his days he said, in more than 40 years, no one has been able to make a clear metaphysical model for what's going on. And this is this measurement problem really kind of personified. Nobody really knows what's going on. We've thought about it a lot, but that's about it. And then Wolfgang Pauli, who's a famous Italian physicist, and he basically said, you know, I'm not sure that we need to think about this. So this is more of the shut up and calculate model. But it's not really reason to rack your brain to understand what's going on than to ask questions like how many angels can sit on the head of a pin. So thank you for your attention, and we're looking forward to more discussions over the next couple of days.
So my question is related with quantum mechanics. Since we learned that quantum mechanics or quantum physics, it teaches us that everything we thought physical is not physical. So can you please clarify this honestly?
Good question. I wouldn't say that everything that is physical is not physical. It's just that all of the things that we think of as physical have a certain reality to them that keeps us from knowing something fundamental about what's going on. But it's not that they're not physical things. The electron itself, there will always be that electric charge and that mass. We know that it's there. It's just that we don't know some fundamental piece about that at some time. And the question is it really there when we don't look at it? That's a really good question. And in fact, that's one of the ways in which some people think a little bit about quantum mechanics. But I would say that it's not physical. the physicality is, if you like, it's kind of hidden from us at certain times.
Chazatanda, ane sujing ngobu kejashi yudu zambala, ane sujing ngobu de sujing imbang anzu ha kugiyo marisidu, ane karsi yor slavin bena sujing ngobu ke neju changma ane anzu ke shingi yor marisigiyo maris. Chitang anzu ke de sujing ngobu ke chechu dinde yor siya de shigi yor deni bena tando ya, ane anzu ke ha mawo ya ke ane chala dia dinde ane mango yungu yoris. Pecha shana ane anzu ke dunten sidu zam dunten sigiyo nere tiga nang shing tanda lokdu sigiyo bena lokdu siya denzo lokdu ke neju dinde de dig kosa dinde yin siya re ke neju mangbo she tur den yin bena ya tando ya ane dig tola ane she matobe ke ane neju mangbo yung digi yoris. Ane tsedungun kamrik bek namsha rodang ton she yung du zambala ane lokdu di kawa yoris sidu zambala ane kosa di jaja jatamba ngebek ton del yoris ya chi she tugiyo marwas ko digam stigla yo sigre siya ki ane keja mishi she tu mewa sonza ane dig tola nganzu sukjin di sukjin ba ha ko ne tando ha ma wo chi la de mangbo yoris ya ki keja di dinde chin le yoris.
Does quantum mechanism ignore logic?
I don't know that quantum mechanics does anything. It's a formalism for thinking about it, but it is logical and has sets of rules that it obeys.
Tsidungun kam ribek nanglola ane namgyung anzu she de ki tensik se joro chiza ane denzo tsime tang yorwe se ki thiwadi kuso chiza ta thiwadi kilela ane tende mares tetang anzu ki sujung ki samlo tang tang da gyunsen ko tang la kewa tende yungu yore deni bana de samji ki tsidungun kam ribek ki namsha ki nanglola ane tensik peju chigi mewa ane gyunsen dotang peju chigi mewa tende mare khoraya ane tensik dotang ji ki thoni she de chagi yores.
What are the main limitations of classic physics?
The limitations of classical physics? The limitations come about, it's more about length scales. So when things become very, very small is when classical physics starts to break down. And it doesn't break down completely, it breaks down in certain particular ways. And so one of them is position, but also our understanding of both position and also the speed of a particle. And how we know that, the energy of a particle, like the discrete energies in a hydrogen atom. And those are kind of the basic places where classical physics starts to break down.
Sujungun kam rigbo nanglo la mandang we cha khari yore se di tiware do sujungun kam rigbo nanglo la mandang we cha khari yore se du zambala ane chike chejung gi che da ringdung gi che de ke je shi yung du zambala ngobu thamu ki ne kap le yung du zambala ane sujungun kam rigbo ki ane de she jak dan den zo shik du yore me wa cha du yore se she ma tu ba cha du yore pe cha sham log du ke khosa si gi yone ane log du dan te wa yobe ki nyorje te ga na shi log du ki chira ba chig le te wa yobe ki ane tanda nyuba shuk den zo ane Tandi Koran can dish Yawananshi and it's sitting in the Yong Siri, Consa de Mange Balaresia, Kitinzu can dish Yana Denzo, Sujung come to dish Yatu Yamar, just over Tamik Sishik Le Yung do Zambala, and Sujung come to dish Yamato near Ratu Yoris.
What is the theory of the quantum mechanics?
The theory of quantum mechanics. Well, classical physics and quantum physics basically are different formulations of how we think about how particles or how objects move or behave under forces. And so the theory is just, in fact, the Schrödinger equation is another version of Newton's second law, which is a very basic formulation. So the theory is basically a way of dealing with understanding how systems will evolve in time and space if things are very small, and using this formulation that the position is indeterminate, or in fact that it can exist in many states at once. And that's really where quantum mechanics is.
Obu Dinzuki Chawachedan, Obu Dinzuki Gugu Dandang, or Dang Obu Dinzuki, any Kosa Kanderesia, Denzu Sama Obuki, any New Zealand Deshiak, Tabshi Chigioris, Lakbord Dutanda Pecha Shavimina, any Schrödingerki, any Tidung Komrik, Namsha Shevik, Nyamzi Yoris, last one, Nyamzi Dim Bimbina, Sujung Komrik, Nangola, and Nitun Kitintim, Newek, Nyamzi, the Chipa Chadu Yoris, in a Manda with the Karchadu Yoris Lavimina, and ngobu tamu ke nekabla le yung du zambala ane chikin deshi jawadi sedung ngam rekbe deshi jawadi ane suging ngam rekbe deshi jamatoya kita dinde ko ne ane sosu samchu mandawada ane deshi jatoya ke seshi mandaw chalu yores.
Maybe I just add that a lot of what was happening around the late 1800s and the early 1900s is that things like looking at discrete spectrum, there was no classical solution to that problem. And so quantum mechanics produced a way of thinking about that. There was also looking at the radiation from the sun and a few other things that kind of spurred people to think we have to redesign a little bit of the rules when we want to talk about atoms.
Pesha vimena tirab chulgu ke me da nishu kun godo dwala ane nima da tima yimbe ke ane ngobudu zo we tro we kapsula we ki ane shell sigro ngon dama chap de sto chap jang di ane kumu to ne che tanji ane chugyu wona shi chap de ma yimba ane tumbu chechen le yong de nang gu yorwa chaza di ngosum cha de yor chaza tinre ke ane we chodang di chidu ngom rikbe kapsula kap thitusla ndeshi ga thu yo mares ha gu yo mares din deshi ga tu me ha ku me we gyumzel te ne sujung ngam rek sing yo mars cheza di sing me wa sonza ani sedung ngam rek pas ya de yong bare cheza sedung ngam rek be ke tadub di lewe ke gyumzel te ne o ta ni me ke we ina re din rek ngobun zo we chowe kapsla we ke shell ke nanglo la ani remo phapang di ani khachi ni yung yo res ya di ani deshi ni yung yo res.
My question is what led to the invention of quantum physics?
So it was a variety of, again, trying to explore what was happening at the microscopic world in very small particles. And a number of different physicists were working on trying to understand this and thinking about some of the problems. But I would say that there's a number of things that were tried. We oftentimes think, oh, here is the theory, but in fact there's many ways that people were thinking about it. This is the formalism that came out in about the 1920s that seemed to be self-consistent and was able to answer the questions about atomic structure and nuclear structure that was evolving at the time.
so khawal thuk du yore sia di thiware do che da che dung ngom rek pa so khachin tharo res la bim bena ane thurab ni shu gun go de din su la ane mi din zu ke ane ngobo thamu ki ne gab la ta dun chen da ane dun chen ki thupja din zu ko thola samno da ya da dak chi che ya ki khogap chung yo song za ane kap thi thus la ane dun chen sia de din de resha dun chen ki to ta din de resha sia din zu ko thola samsu mangbo ju yung yore samsu mangbo de kap thi thus me su su ki samsu manda yo sir de ne ina yang khale khale tu zu dorim shin de ane khonzu ki chi ngo la pa nyam chi ngo la ane babya din chung ba de di pa wa chung sa ane thumong ki ane ta samlo din zu da ane thumbe ki ane chi kin ro tan chi chung wa song sa chi kin ro tan di shila sha ne she sha be ki nam sha de lang du chi dung ngam ri be nam sha si yores.
Yeah. So I think what was happening in the early 1900s, as you know, Ted was mentioning about things in classical physics being infinitely divisible, that you can take something and divide it into smaller and smaller and smaller units. It was becoming very clear around the early 1900s that if you did that with energy, where you took some amount of energy and kept dividing it into smaller and smaller units, in principle, then the results that you were getting experimentally were not compatible with that view of energy. And Max Planck was the first physicist to point out that energy, after a point, cannot be subdivided into anything smaller, and that smallest unit of energy became the quantum, right? So that was the first understanding of the word quantum.
Gela Ted Korangi any gajeshe shawa de la nembeji janas ta tirub jugu ki any julgu da nishu kin gotu kin la ane midin zuk samlo khartang gi yores lavin bena ane phemje ki ngobo im benre di mayim be ki nubado zuk thang khar ngazu gobshe gyavin bena ane bed gobsha mu tune bed chungdala tuya mewe ke che phardula ane gobshe gya thugre samya ki ane samlo di yores ta dinde ki samlo ji ki che ane takchi chiga dodu sambala ta thurab ku nishu kin godu dawala ane thurik da dinzu yarge chimbe gyumsen tene ane ngobo thamu nuba peshana nuba do im bena dinzu ane bed thamu shi uchi che shi ki phardula ma gobshe gya do thubdu sambala kap thi tu su gobshe gya we kapsla ane takchi ki nanglo ya ngong ya deda dingla ane suyung ki ton samlo tangdu sambala nuba dinzu gobshe gya na dinde ji yungre samya ta ge yungu yores yoris pesha shana ane nuba thamu denzo ane tuzu chikle ledu sambala dile la ane gopsha ya mewa dile cha la ane cha che mewe ke ane seshile le yungdu sambala dende ke ane thirdu ke seshi sigyo ne thirdu ke nube ke thum kongu chungyung dende chikla anganzo quantas sigyoris quantas ye ken thani dile shicha je ta sedu se le yoro cheza di tharwa sonza ma explain the khunju ke serik ba khunju ke shegyore cheza khunju ke samju di shila shane an tanda sedu ngun kamri be namsha se di ane sheja mangbu chikla chap de ke namsha di chungbar chadi yoris.
Bryce, can I just
yeah,
do
please.
one? I think there's something else. Ted was also talking about Niels Bohr and his model of the atom. I think we can link a little bit of the stuff that we just talked about, the quantum. If you think of the atom in the classical sense, so you have a nucleus and you have an electron going around. If you just apply classical physics, it turns out that the orbit of the electron is unstable, that it will eventually fall into the nucleus and be gone. But that's not what happens. Atoms are stable. So that was one of the first indications that something about classical physics, when applied to atoms and electrons and nuclei, does not work.
Tiganashi Tanji Gented Koranki, any Dundrinki, any Keja Shev Kapsula, any Neil Borsi, sitting but Dick Shesha, Dundrinki to lunch Shes was. Chazada Sujin Samutan Chevi, Bena, Dundrinki, any Namshak Nangola, any Kimala, any Dundrinki, Nindusi Diore, Tedusi Diore, Dintal Loduk Korakur, Loduk Korakur Kapsula, any Janta di, any Kandeshi Bena Tigris, Ringdula, any Chewa Yomaresia, Dig Sujin Samutan Diores. Chazada di Jela Kunzukatashi, Ushi Yundu Sambala. Ane dindrek ane dindren da logduning part jangta di ane khangyi mai ba di ane thumbu sechin se yowa ane dindrek jangta di khangya rungwa ji shav yimbe na tuzu chikle le yungdu zambala ane logdu dinzo ane dindren tedu nanglo kora konne de dewa mai ba nangla sa che ane dindren shikdo ya dindre yonggu yore sina di nguyo ni sul yongdu mewa songza ane sujun ki ane dreshi jangta di ane mandangwa chama sangwa dindre ane tokshep chungyo tokshep chungyo ki gyumzen la ten ane sawa chidung kam rikwase di thargoya gyumse chikdine chadiyores.
Thank you for the explanations for so far away. We understood what is quantum mechanics and what are quantum physics. But I would like to place a question like, what is the purpose of quantum mechanics?
Well, I think the purpose of any scientific theory is for us to gain a deeper insight into the way in which the universe works. And so the purpose in this case is that we've developed a theory that allows us to explain the details of atomic structure, of nuclear structure, of how energy is created in the sun, which you can't understand otherwise, and a whole variety of physical problems that without quantum mechanics you'd be unable to do. So I would say the purpose is to understand the universe and to understand how it works.
Zidungam requested the Gosu Sosta Hinea, Zidungam requested the Goba Carrier, Sien, Goba Carrier, the Tiwa. That Zidungam requested Goba Carrier, Sedu Sambal, the Zidungam request Mare Siriki, and Ripa, Dumshi Sama, the Chikwaris, Karis Lavimena, and Shingubuki, Nizu, and Chasang Shia, Mangs Shia, Nizu Sawashin, and the Chadi Yoris Mudi, Chaza, and Dundrenki, and Namsha, Dundrenki, Nango, give it, Tidu Controta, Tivanashi, Tidu, the Dundren, Jevik, Tone, and you make Nangola Nuba Kandis Jungur, and you may Kandis Tigioresia Denzo, and Sedung Gamrik, Nizu machine being Bena, and Shian Tapio Maresata, machine Ubotamuk, Nakeups La, and Nizu Mangbujic machine by Shendo Check, Chedola Sedung Gamrik was the Chungores.
Okay, let's hear a question from the audience. Yes, please.
I have two questions. The first one is that you said atom is the smallest particle. So how do the scientists make this smallest particle so powerful to make an atom bomb? That's my first question. My second question is there any agreement or disagreement between the quantum physics and the Buddhist way of explaining particles?
Okay, so the first question about, I think, is how do you make an atom bomb when you have atoms are so small? Or something of that nature. Does that sound right? Well, when you light a piece of wood on fire, you get some energy coming out from the wood. And the energy that you get from burning a piece of wood or a piece of paper comes from taking atoms that are connected to each other and pulling them apart. And so you release a little bit of energy, and it's called chemical energy. Atom bombs work on a slightly different, they take the energy of the nucleus. And so in the nucleus of atoms like oxygen, there's 8 protons and 8 neutrons. And to pull those protons and neutrons out, if it's a small atom, it takes energy to pull them apart. But in bigger atoms, like uranium, if you pull them apart, you actually get a lot of energy out when you pull portions of them out. And the energy is thousands of times bigger. It's much, much bigger than chemical energy. And so atom bombs work on the energy that it takes to bind the nucleus together, which is very strong. So that was the first question.
Dirda, ta dunjen se di chunju shiu junas, dunjen chunja se nuba chimbu dinde khande so tu yores la ta thiwa thangbo di. Thiwa niwa de jeli gula so. Chasa di khares la bimbe na namgyu nganzu ane sing da ane ta di mai be ke ane physics rig den so meta tang kapsula nganzu kharchi gi yores la bimbe na dunjen de so chetan jar di yores pa so. Jar dewa di pha khate bimbe na khate we ge gyumsen te ne kira nuba jirai res. Sing meta tang yu sambala sing ge thubji ge dunjen de so khate du yores. Di ba sonzan kira thöge make thöti yores chesa di nuba de chunju mi shi yomares. Dunjen chunja nang lo kira kharchi gi yores la bimbe na dunjen ni jar dewa tan da logdu gi jar girwa. Di pha khati gi yomardas. Dunjen ki nang lo le yebe ke te du se te ning se nucleus se di kachi gyores chena pecha shana ti dunje ane mandala ane tedu ke nanglo la podu ke thanga da phardu ke thanga manda yore soglung do shim bena oxygen sigro di bena nanglo la ane podu thu ge da ane phardu thu dinde yungu yores chena ta dinde ke dunje jigo cheshu tanda ngzu dunje sunche soya di uranium se din zoro chena ta dinzu ane tedu khora pa khapsha tanje ane podu ke thanga di ane pator sha bena ane nuba chimbu shiu chirai res chena ta dinde ke ngzu dunje sunche nanglo la 유림님 기 띠두 torche ane nuba mangbo chidu chigyo chesa nuba mangbo chidu chewa dila manzo kharsi gyo slavim bina dunjan sunge sigyo res.
Can I ask you to turn your mic off if you're not going to ask a question? So just push the button. Oh, maybe yours doesn't go off. Hey, and we have a question from the green team over here. So from the green team.
I have read somewhere that atoms are almost 99% empty, no? I'm also made up of atoms, so does it really mean that I'm almost not here?
Yeah, in fact, in atoms, in all atoms, the amount of empty space in an atom is much, much bigger than the amount of space that is occupied by the constituents. But of course, they're all rubbing up against each other and they form all of the pieces of who you are. So yes, in fact, you're mostly not there.
Thank you, sir.
Theodore Hodapp bimena ane nge khoya chi bimena dunten sia di jaja ane gubju khogus nang tongba resik dus chesa ta nga dunten thuba res nga dunten thuba che dunten denzo jaja gubju khogus tongba ina ta nga peche wa tongba re dos ta nga jingkhang na din chokna dinal me wa res se ki di thewa re do chesa ta di res chesa ane dunten sia di nange ane thubje ki tanda phadu da phodu sia dinzo chi bimena dinzo chu khorang che jung chi bimena pa chunju shi wo jaja gubju khogus an tongba cha di yores chesa samno tang din je thon tang bimena ane kirang peche wa di tongba res ta yo mare samgudna yo marista.
Any more questions from the audience? Yeah, right here, blue team.
Yes, I have a question. Like quantum physics, it has been introduced lately, but what about the laws and theories which have been introduced before quantum theory? Does that, by the introduction of quantum theory, does it affect the all the theories which were before them, or like the laws?
Very good question. So anytime we do a new theory, whether it's quantum physics on top of other physics, or anytime we've improved all of the physics that we do, there is a rule basically that says that the new stuff has to explain all the old stuff too. And so classical physics, which existed before quantum physics, all of classical physics is still valid. It's just that when you get down to particular regions, that the rules change a bit. But there is still a mass of an electron and a mass of a proton. Those things still behave in gravity, for example, in the same way that they do in classical physics. But the interactions that occur at very small things, they do change. But that's true of all kinds of things in terms of physics that gets invented as you go along. But they're still valid. Has to cover those things, but in different realms. So classical physics still works in the very big, but in the very small is where it breaks down.
Theodore Hodapp Cedur ngongkam rikpa mother wikingwala sugi ngongkam rikpa yodigore sugi ngongkam rikbek nanglola ane timda ane ta tensik mangbo yodigores cheta ta cedur ngongkam rikpa thar yungdu chambala dingwele yodebeke ane timda tensik dinso kharchigi yore sle ditiware do di lendela cheta ane cedur ngongkam rikpa re dimaimbeke ngongkam tan serike ane rikpa khandi chimbena rikpa sawaji thar yungdu chambala rikpa sawa dike ane ngame ki shesha weke ane rikpa dinso kin deshe gap to weke nizu dinso changma she topic gangla ngar ki she ma topic nizu langma dende ane she guwa chagu yores cheta de la sambala sugyun ki nanglo lan tenshu ki namsha shesha wa tigana shin gugyu ki namsha shesha wa tindeng ke doze kol ke je shesha wa dinso changma ane sedu ki nanglo la she gu yores tigara ne dig yores ina ya ane ma ship char dobin bena ngung ki she ma tu ya dende ane sawa she to guwa goya she tobia dig to ne ane juwa thamu do de dende yung yores.
So let's hear from right here.
Just have two questions, very layman stuff. How is this E is equal to mc square related to the quantum and the classical physics? So that's my first question.
Okay.
And the second question is regarding this non-localization. I sometimes see in the YouTube non-localization of the particles, you know, how it influences a particle at long distances. I mean, whether it's a reality, because on the YouTube it can be a little bit of it.
If it's YouTube, it must be correct, I think. No. So E equals mc squared, very famous equation from Albert Einstein that equates mass and energy. In fact, that's actually related to the question of the atomic bomb, in which one way to think about the energy that's released in an atomic bomb is that you have less mass later on, because that mass is turned into energy. And so I would say it's really conservation of energy in some senses, is that you always conserve energy there, but in certain kind of reactions where you'll actually change the mass of the nucleus, which happens when you split it up. That mass, the mass change, if you were to weigh the constituent parts of those things at the end, you'll find that the mass would be less, and the energy is the energy that's released in an atomic reaction of some kind. So it's really, but that applies to everything, is that you can equivalate mass and energy by this reaction. And the second question, I think I'm going to ditch. I'm going to kind of duck, because my colleagues are going to talk about that one actually coming up when we talk about non-locality.
So my question, first question, the second, there was a small part to it.
Okay.
Because I wanted, where does it stand in relation to the quantum mechanics? How does it stand in relation to the theory of quantum mechanics?
E equals mc squared.
Yeah.
So relativistic quantum mechanics, which is a little bit more complex than regular quantum mechanics, obeys all of the rules so there's a certain version of quantum mechanics which obeys all of these kinds of things. And this equation will apply to quantum mechanics just as easily as it applied to classical physics. So there's no variation in there, but there is a slight difference in the theory when you get into relativistic behaviors there.
And the energy would be discrete, right? It'd be steps.
Yeah, same. You still get discrete energy levels, for example, if you have that, but this applies to more broadly, actually. So.
The Gela Kurang Gitiwa the Tanda Albert Einstein Kishawiki and Yamzi Kerachim Bojero and a new EMC E school to MC square say dig and a Tidung Comric but Tewa Kandejores, the Tiwa Tangbordoa. Jadadi Jada and easy the Nuba Sigures. MC di khar sig yoris lavim bana ngobuk doze sig yoris cheza da di thiwa di khar da dewa cha yoris lavim bana dingwen la dunjen chun ge soya ki thiwa di da dewa cha du yoris cheza dig nang lor khar cha res lavim bana ane dunjen chimbu ji dus che ane te du tor yung du chambala ane te du tor simbe ki ane lhagma ki du ngobu dunju nang lor la ane ngame ki ane dunjen dik nubach doze ane chung ching yoris dila du khar ching yoris lavim da ngar yebe ki doze di thanda ane nube ngol chi nuba di ane ba da chimbu shu ma ane chedu di chadi yor cheza nuba sia da ane pemje sia dini ane ngo geru imba dila du zambala thanji ane nuba nyarza ke tentim sia keje she so cheza ane dida chikba chadi yor tega na shi ta EMC square sia di ane serik nanglo keje she yu du zambala tudub ke namsha si yor tudub ke namsha shela shawe ke thone ya chedung ngam rikbe ke namsha she yor cheza di ane sugyung ge ta ina ya ane tanda ane E school to MC square sia di ane nuba she dev kapsla nuba denju changba ne thumbu chechen ma do muntune yungyo mares ya chedung ngam rikbe shedan denju ta gigyo mares chikba cha yores.
According to quantum mechanics, if the position of the electron is indeterminable or unknowable, then the object which is made up of a group of kind of like atoms. And in the classical physics, the position of the object is definite and absolute. So how can we come to the conclusion that an object which is made up of many atoms, the position of the group of atoms is kind of like definite and accurate when it's kind of like which is made up of group of atoms is not determinable?
That's actually an extremely insightful question, because quantum mechanics, the theory says that it should apply to objects at all scales. So from atoms to molecules to macromolecules to to cats to you, right? But we know from our everyday experience that there comes a point at which objects don't behave quantum mechanically. So something is happening in the transition from the quantum world to the classical world, right? So when enough particles get together, or enough atoms, enough molecules, then somehow that system starts behaving classically. So it has a definite position and it has a definite location. But we cannot explain from the theory of quantum mechanics exactly where that transition happens, and that is an open question. And at this point, physics can't really answer that very clearly as to when the transition happens from quantum to classical.
Hello, yeah, okay. Tiwa de be agu dus. Tiza da tiwa de khare sha slavi bena kerang ki tanji keje she ki nanglo la. Ane tanda logdus le sodo da tigana shi ane du thamu den zu ki ane khosa mangi ba res. Khosa mangi ba yimba zam phasha maze ane kerang ki ane she tubrung mares. Ha ko tubrung mares ye ki ane keje she soas. Tiza da nganzu mido shimbe na ane nganzu dinde ki ane khosa ha ma go nye da ane she tubrung ma yimbe ki ane dunjeng ki tupsha ba den zu ane khosa nge ba da ane de lo se zuzuye gyo chade doas cheta di khandis chungbare se ge tewa di ane genla ki len khar gas lavi bena dine res cheta ane sedu ngam rigbi ki namsha di ke ngobo thara changma la ane deshi gya thubu ye sig yores thubya ki ane namsha chi hin sig yores ta kharcha di yores lavi bena ngobo thamu ki nekapsla ane khosa mangi bada ane thanda gushuk mangi ba denso sangma ngobo rakbe kapsla ani ngeba cha ru yores di ngobo thara ni ki namgyur tensu di khares labe bana shingmobe ki ani namgyur tensu ki dendun je cha di yores ina ya cheza ta dende ki ani thamu ki negam ne ani seshi ngechen chi lu gyur yale ingdu sambala namgyur ten thang di ani khajin gyur du yores mangi ba de ngeba khajin cha du yores ha mawo ye di ha ko tubru ni ba khandes cha du yores du sambala kharchine se di ani thanda imbe no mene ya ani open question la du sambala ani thanda tewa neme gyo chadi yores suk gemna di yor cheza sedung ngam rikwe nanglola ani ta hamawo ni si ne re dishi gyamato ye okay ani nezu de zo chadu yores.
Maybe I'll just add one thing to that, which is that the indeterminacy of the position of an electron, we still know that the atom is there. And when you put two atoms together, or 3 or 20 or 100 atoms, we still know that they're there. We might not know exactly where this atom or this electron is within that atom, but we do know that all the atoms are there together. And so even though there is some indeterminacy in the position, we do know the determinacy that there are atoms there, and they start to form macroscopic objects that we can actually see and do experiments with.
Chizata dishi sigi yoro sanzo dunjen chimbe na dunjen chik nanglola ane tanda logdu dunzo kawa yore siya di ane nge tubu yor mares dik chala ane hako matuwe ke cha yor din imbe na ya dunjen dik nangla logdu yowa di nganzu ki nge tubu yores hako tu yores. Chizata dunjen ki ane gyumzen tene dunjen dunzo nganzu so ruru soche ane sokpa su yung du zambala sokpe ke kongu di ane kosa di nge se cheru chinche ane tama seshi chik le yung du zambala o dela du siya di ane she tuba cha du yores.